Welcome to the SC4x Hangout. I'm here today with Lex. My name is Connor Makowski. I'm the digital learning lead here at the Center for Transportation and Logistics. So a lot of the things that you'll see in the course I've been working on, for example, the different sandboxes that you guys are now seeing be put into the courses. Those are a lot of the things that I'm currently working on. So I'm here to introduce Lex. And Lex is actually currently working with the AgeLab to help develop autonomous and semi-autonomous vehicles. He's working in machine learning and artificial intelligence. He's actually one of the experts in the field. He's going to be teaching a class here at MIT on that pretty soon. And a lot of what he focuses on is the interaction between the people and the machines, as well as how the machines interact to the road. So Lex, I'm just going to give you the floor here and let you get going.
Great. So thank you for having me here. I love talking about this stuff, and hopefully you guys love learning more about it. We're mostly using learning-based methods, so machine learning methods that use data in order to figure out how to create artificial intelligence systems that operate in the real world. So that's in the cars. We want to build autonomous, semi-autonomous cars that use data to learn how to perform better and better. Safety is the most important thing in driving, but also providing an enjoyable experience is secondary, but also extremely important. So I'd like to talk today about some of the machine learning side of things that we use, how that can apply to autonomous driving, and then further to other domains and supply chain and every domain that has numbers and data. But start to talk about data. So one of the things that's essential to all machine learning problems, all machine learning approaches, is large-scale data. So hopefully you're seeing the screen now, the set of vehicles that we have, we're collecting data from. If you folks are familiar with, there's a car called a Tesla Model S, Model X. Tesla is a company that produces cars that have some degree of autonomy. So we have these cars are able to autonomously control themselves on the highway and even in urban environments autonomously. They steer, they take in video from the forward roadway and are able to control themselves.
And so you're collecting data on this, correct?
Yes.
So how are you collecting that data?
So we've instrumented. We have 24 Tesla vehicles. These are $100,000 plus vehicles that we have grad students tear apart to instrument. So we put cameras inside the car that record everything about the driver and everything about the external environment. And those are just raw pixels that we're collecting, synchronizing, and those raw pixels put together form data, a data set, the largest at MIT in terms of size.
How big is it?
So it's now 200 terabytes of video data, and that's compressed. So uncompressed, that's about 100 to 150 petabytes of data, which is multi-million dollars of just storing the data. So that's a lot. That's truly big data, but it's useless as raw pixels. We have to be able to have algorithms, machine learning, computer vision algorithms that extract knowledge from that data. So every day there's shown here 500 miles plus. We have cars driving all over, all this data coming in. Then we offload it from hard drives, put it on the cluster, and that forms the data set based on which we train all our algorithms.
Okay.
So I'd like to sort of talk a little bit about the big vision of the subset of machine learning we've really focused on, which is called deep learning, which is using neural networks for achieving some of the stuff that I think students have already been thinking about and learning about. The neural networks is a very special kind of machine learning, and I'll talk about it's able to automatically remove some of the effort that humans have to put in up front in order to extract features from the data. So neural networks are able to deal with raw data a little bit better than other approaches. That's the unique quality of neural networks, as opposed to bringing in experts in the field to figure out what are the interesting features in the data. Neural networks are able to take just the raw data and extract useful features.
So people aren't having to code in these exact items that are required, so the network is able to learn some of these features and to build from that, and no specific coding is necessary.
That's right. So for facial recognition, that means previously you had to encode the concept of a nose, ears, eyes, eyebrows, mouth. The neural networks take in hundreds of thousands of features that aren't encoded by human beings about the face, that are useful to perform the face recognition task. In the same way for any other kind of data, it's nice to be able to remove a human to some degree in that big expert, some degree up front where those features need to be coded. Now the question is to which degree the human, quote unquote, can be removed, in the sense that how smart can we make these machine learning approaches? Are they limited? Are they limitless? So far, we've been able to do very specific tasks with machine learning, like for everything from playing formalized games like chess, to solving medical diagnosis based on images, to interpreting what's in external scenes, so detecting pedestrians when driving, or extracting patterns in the data of all kinds, any kind of numerical data, including all the supply chain applications. But are we able to take the next step and create a more general purpose system that is able to figure out higher order ideas in the data, insights in the data? So far, we need grad students and brilliant people with PhDs to extract the true insights. And so that's the question that a lot of the folks working on machine learning and deep learning are looking at. So shown here on the slide on the left are the sort of quote unquote teachers, and on the right are the students. So who is teaching the machine how to interpret patterns in the data? The teachers in what's been most successful and stuff you've been learning about, I think, so far, is called supervised learning, where the human being is the only teacher, meaning in order for a machine learning algorithm to operate successfully, you have to give it ground truth data in the training process. You have to teach it what a cat looks like, what a dog looks like. So every piece of data for a classification task, every piece of data has to be matched with a human attached label that allows the machine to learn how to map the data to the label.
Do you do any of this in the AgeLab right now?
Yes. So everything that's successful in machine learning is primarily using supervised learning. So if you want to detect pedestrians successfully, what we're doing with AgeLab with autonomous vehicles, detect pedestrians, detect lane lines, detect other vehicles in the forward roadway, you have to provide it a lot of human annotated labels of what a vehicle looks like, what a pedestrian looks like, what lanes look like.
So there's someone that's sitting there on a computer looking at this and identifying these things for you, which then the machine can learn from, correct?
Exactly. So a lot of the investment from companies, a lot of the work we're doing is collecting the data, step one, and step two is investing hundreds of thousands of millions of dollars in the actual annotation process. Where a lot of human beings are sitting and clicking on vehicles, clicking on pedestrians, and so on. That's sort of sometimes the unspoken, messy detail of machine learning is currently our systems are not able to efficiently learn from the data in the same way humans are. The efficiency of learning algorithms is orders of magnitude slower. So for us as human beings, the amazing thing about our brain is all we need is one or two examples of a particular idea or object, or visual characteristic of an object, to learn the concept of that object. You only need to see a cat a few times in order to be able to then generalize the concept of cat in order to detect it in future images. That's currently something machines can't do. They need thousands of examples of cats in order to figure out in future images to detect that task.
So in the future, do you see this kind of going down this human input as the machines become more able to identify these things and make generalizations based on less and less data?
Right. Yes, exactly.
Okay.
I see the future, the excitement of machine learning community is in letting the computer, the algorithm do a large percentage of the figuring out what's going on in the image. This is where deep learning comes in it's called representational learning. It's learning how to the fundamentals of the visual characteristics, the physics of the world underlying the image without having the human encode that physics. So the human only helps sort of the same way you can think of it as parents help when you're first growing up, when parents help teach a baby, a child, as they're coming up, basic concepts. We see that's the role of the human being should have in teaching these systems. Otherwise, it's too costly financially and effort-wise to involve the human with the annotation process. And that's where reinforcement learning and unsupervised learning really come in. These are this different branch of machine learning where most of the work is done by a machine. So, and just to give you a brief view of the world of machine learning, what can you do? This is sort of a little bit of a philosophical, but also a practical question of what kind of things a machine learning system can take in and what kind of outputs it can produce. Really, anything that can be converted to numbers or vectors of numbers or sequences of numbers is what a neural network or a machine learning system can operate on, and it can produce in the same way numbers, vectors of numbers, and sequences of numbers. I'd like to give a few examples of what that looks like in various domains. But first, a quick comment about the deep learning methodology and what it is. And it's inspired by artificial neural networks, inspired by real biological neural networks, where our human brain has about 100 to 1,000 trillion synapses. These are connections between individual neurons. And our state-of-the-art neural networks can only have about 1,000 to 10,000 times less than that in terms of connectivity. But the idea is the same. The basic computational unit of a neural network is inspired, modeled loosely, I should say inspired by our biological neuron. The input, the computational, it's beautiful in the sense that it's really simple. The individual unit is extremely simple. When we combine it together, it can be arbitrarily powerful.
Mm-hmm. Hey, do you mind hiding the box in the bottom of your screen there?
Sure.
Let's get that so the students can see the full slide.
The full slide.
Yeah,
sure.
absolutely. Thank you very much.
Yep.
So this is inspired by actual neural networks. And so what ends up happening is you're choosing whether or not to fire some signal. Is that the idea here? Just like a brain?
Exactly. The idea is, as you see here with a little video, there's a neuron has a set of inputs and a single output, and it assigns weights to those inputs and sums the inputs together and puts it into a nonlinear function. That nonlinearity is where the magic happens. So what it's doing is you're teaching the weights are the things that the neuron is adjusting, and the task for the neuron is to learn to get excited at certain concepts and not excited at certain other concepts, to disambiguate, to separate concepts. So you can think of a neuron, and sorry, I keep going into cats and dogs.
Absolutely.
It's the easiest example. Sort of, you can teach a neuron that gets excited is tasked with determining the difference between a cat and a dog. So that neuron assigns weights based on certain input features, which would produce a very high output signal for features associated with cat and very low output signal for features associated with dog. And when combined together, you can start to learn arbitrary concepts in this way.
And so then it's actually learning how to fire the synapses and what to look for in the image, exactly, or what to look for in the system. So in this case, one of our students is asking, do you mean that this is completely untrained learning in this sense? Or what's happening here?
So the internals are not human supervised. So this adjusting of individual weights is not adjusted by human beings. This is where I mean by representational learning. It's the internals of the network figuring out what features are important for classifying a dog or a cat. That's done by a machine. That's automatically optimized. Those weights are adjusted. The high level concepts, that's where the human steps in and provides examples. For example, in images, examples of different objects, and the network figures out the weights to tell the difference between those examples. That's called representational learning.
And so there's something inside this network that's saying, I'm either going to kind of activate this thing or I'm going to turn it off.
Exactly.
And so that's where you're not programming that in.
No, you're not.
It's just saying, if this is correct, make this a better activated function. Yes. And if this is incorrect, make this less activated, exactly, less of a neuron firing, so to speak.
Yes, and so as an example, again, I apologize for all the pictures of cats. It is the most popular concept in computer vision, is using cats for all of these examples. I think here's an example of how a neural network learns. So first, there's a forward pass. You provide an image. It doesn't know. It's just a set of raw pixels to the neural network, and its task was saying to classify cat versus dog, and randomly. So in the very beginning, the neural network knows nothing. And it just, based on the weights it currently has, randomly figured out weights, the network produces the classification of cat. And then the backpropagation step, this is how the network learns, the backward pass through the network. If the classification is correct of cat, this is where we need the human to say, is it correct or not? If it's correct, then the signal, there's a positive backpropagation. The signal that resulted in saying that this image is indeed a cat, all of those weights are increased. All the weights that said it's not a cat are decreased.
And so the machine is then saying, okay, things that are saying this is a cat, then have extra value. Things that say it's not a cat, then have extra almost negative value, pushing it the opposite direction.
It's an extremely simple step, so computationally, but when nodes are connected together, there's a beautiful theorem that says when there's a single hidden layer, so a network with 3 layers, it can learn any function, any mathematical function. Meaning all of us in this room, all of the people listening, can be modeled by a neural network with a single hidden layer. So it's a fascinating look into the power, the representational power of these things. So the individual unit is extremely simple, but when put together, it's really powerful. And so another example, so you have a picture of a dog here. The network doesn't know that. It still says it's a cat based on the weights. And then so there's a backpropagation signal saying, no, no, no. Everybody that said this is a cat, their weights decrease. Everybody said it's not a cat, their weights is increased.
And so then it's telling the system to do this. And if it does this over many iterations, it begins to actually learn how to classify that. Is that correct?
Exactly. Okay. And it's one of the exciting things that the current neural network approaches are achieving state-of-the-art results. They're breaking all kinds of records, just orders of magnitude improvements in performance on image classification, voice recognition. For most, if you're using a smartphone, if you talk to your smartphone, the voice that goes into your smartphone is processed by a neural network in order to figure out what it is you're saying. So some of the problems in machine learning have seen incredible improvements because of neural networks. But it's not right for everything, and that's important to understand. The thing that neural networks are really good at is, as I mentioned, representational learning. This is the key step I think that we want to highlight that separates it from the other machine learning methods. It's able to, what's shown here, if you're tasked with drawing a line that separates blue circles and green triangles, it's very easy to do depending on the representation, and very hard to do depending on the representation. So if you just take the Cartesian coordinates, drawing a line is impossible to separate the blue and the green triangles. If you look at if you map that same data into polar coordinates, a simple trivial transformation, you can draw a line very easily. The thing is, for other machine learning methods, you have to have an expert step in, a human expert, and says to remap, to do that feature extraction, that remapping. Neural networks are able to help with that step, help figure out, is there an efficient way to represent the data so that you could classify things.
And so that would be one of those hidden layers, so to speak, right? It would be re-representing the data in a different form that can be better understood by even the next step or the steps after.
Exactly. Okay. So the earlier layers figure out the representation. The later layers are able to use that representation to make correct classification, estimation, prediction. So, and just to give you some examples of what we can do with these approaches, what this toolbox allows you to do very well is arbitrary image classification. So I give you an image and you figure out what is going on in that image. We're able to achieve better than human level performance, which means machines are now able to do better at figuring out what's going on inside the image given to it. But here's a famous ImageNet, really one of the early breakthrough sources of excitement for this particular branch of machine learning, is being able to figure out in this large data set of images with thousands of categories what's going on in those images. There's a leopard, there's a motor scooter, container ship. We take it for granted how amazing this task is for human beings to be able to do. We take our vision system for granted. It's actually an incredibly difficult machine learning task. Computer vision is very difficult.
So how big would this neural network be?
So size of neural networks matters. The bigger the network, it takes longer to train, but almost always results in better performances. So For some of these networks, it takes months to train.
Okay.
But once trained, the actual we're passing in an image and producing a result can be achieved in just hundreds of milliseconds, if not just milliseconds.
Okay, so once it is trained, then the ability to classify in the future is really high.
Exactly.
And so that comes into the real-time needs of driving a car. That's correct, right?
That's right.
And so you can't necessarily learn real-time, but once you have learned, you can then apply that real-time very easily.
Exactly.
Okay.
The real-time application is key. So the training takes a long time, but real-time application, it's called inference. So running the neural network is really fast.
And so that's one of the main benefits then of doing a lot of deep training.
Yes, upfront, you do all the investment in the training upfront, and then later pays off by being fast in real-time operation. And just quick examples of other things you can, as opposed to classifying the entire image, you can separate different objects inside that image. That's called image segmentation. You can do the same thing in video. Here shown something we do a lot of in the driving scene. Up top is the raw video. On the bottom is it's called again image segmentation, full scene image segmentation, where the pixels are colored based on the prediction of what that item is: trees, pavements, roads, road markings, buildings, sky, bike, the things that are important for a car to correctly identify in order to plan a safe trajectory. Then there's object detection. Object localization is the efficient, it's again sounds sort of trivial for us human beings because we're so good at it, but as opposed to figuring out what's in the image, exactly localizing where that object is in the image, is doing that efficiently. So you can do it in faster than real time is really important. And that's called image localization. And with that, you can do things like on your phone, mostly you can do this real video to text translation, and then video to video translation, where you put your phone, the input is a video of, for example, here, a box of cookies, where the original language is in, I think, German. Not sure. I apologize if it's not. But it's taking in the raw video, extracting the different letters. That's the classification task. Then converting the letters to text. Then translating the text, again, with machine learning. That's called machine translation. And then mapping it back to text in English. So converting it from whatever the source language is here to dark chocolate translation.
Until you can see the world differently.
See the world in the language that you're most comfortable seeing that world in.
Absolutely. Do you see anything happening with, like, say, virtual reality here in the future, or even like where you can have audio, something like that, where you can actually like go to a different country and then just hear that language in your natural language?
That's right. So that's a great application that's also being done. Real-time translation in audio. So virtual reality and augmented reality, there's a lot of exciting applications in this domain. The trick is, the big challenge is the thing we mentioned before, the real-time operation, making sure the latency between the raw sensory input and the actual output, the actual output of the data is so short, so quick, that when you take that information in, you don't get disoriented by the lag. So that's a technical challenge, but it's one that people are solving very successfully. And you can start generating, so because you form a representation of different images, you can start generating other content based on the source image. So here's a popular application of taking old movies and recoloring them. Or the recoloring of images, recoloring of video is something that neural networks can do quite easily. The same kind of structure, as opposed to mapping to a classification, you're mapping to a set of raw pixels. And you can generate text. So there's a popular sort of methodology of character level text generation. This is, from an AI perspective, a beautiful and fundamental set of results where the input to the network is just a set of characters. The network itself has no concept of language syntax. This is the whole field called natural language processing. So as opposed to modeling the grammar and the syntax of the language, it's able to just take in the raw set of characters. So you can read Shakespeare and learn how to generate characters based on Shakespeare. And the beautiful thing here is that it's able to generate text that actually sounds, is first of all readable, makes sense syntactically and semantically, and sometimes produces quite interesting results. Here, for example, if you start in typing the meaning of life is, that's the human input, and then have the machine continue. And us academics, I think what machine has completed is quite clever, is the meaning of life is literary recognition. And the other completion is the meaning of life is tradition of ancient human reproduction. So there's a lot of sort of humor and interesting results, but the most important thing is the machine is able to automatically find the patterns in language in order to generate successfully that language.
So this would then be a representation of the language that it learned from,
Yeah, exactly,
and not necessarily the meaning of life.
Yes, exactly.
I'm just trying to say that this is what it's learning from essentially, and it's almost mimicking that or thinking of that's the examples that it has to move forward. It's not necessarily synthesizing something completely out of there. There's basis for what it's saying, correct?
Yes. So, but this is also the philosophical open question of all of artificial intelligence, whether the mimicking of intelligence is not itself intelligence.
Mm-hmm.
So whenever the machine, this is the famous Turing test, whenever the machine appears to be intelligent, is it truly intelligent?
Mm-hmm.
And we tend to be very human, discriminate against machines, being very humanist by saying that well, the moment we understand how the machine works, we say it's not intelligent.
Mm-hmm.
But if it exhibits certain interesting qualities, it's difficult to say on a philosophical level where the machine doesn't understand the meaning of life.
Mm-hmm.
So it's a very fascinating area that we're exploring. The better and better these machine learning algorithms get, the more we're able to think about the essence of what intelligence is.
Mm-hmm. Absolutely. So, yeah. I mean, I was expecting the answer to be 42.
Yeah, exactly.
So
exactly.
In pop culture, if you Google the meaning of life, 42 comes up, and it's a reference to a movie. But I think it's very interesting to see how this different kind of concept gets pulled out of like our actual natural language and what's written and what it learned from.
So one of the things just to mention, 42 is you're sort of exhibiting the usual human characteristic of humor,
Mm-hmm.
which is one of the hardest open problems for AI systems. Is this really, that is the frontier of humor, of expressing, understanding emotion,
Mm-hmm.
being able to convey it. That is something that machines are not very good at currently. Able to translate language, but to exhibit cleverness, wit, and even understanding of common sense. That's the open problem of,
Mm-hmm.
A lot of these machines. But that doesn't mean they can't have a tremendous amount of impact
Mm-hmm.
on society, and that's where driving comes in.
Okay.
So here's an example of us taking a raw video. It's called end-to-end learning, where the mapping is from the raw video input, and the output is the steering of the car. So we're able to control a vehicle over hundreds of miles. We have a lot of demonstrations of this. You can check out on YouTube of driving, or the vehicle is controlled either by the neural network or by the internal systems of the vehicle.
Okay.
And this is just an example of that myself inside a Tesla Model S vehicle, where the pink line is showing the control of the vehicle based on the neural network, and the cyan line is showing the control of the vehicle based on its internal system.
Mm-hmm.
And we can switch between the two and compare. And we call this arguing machines, having multiple AI systems in the same car, arguing against each other.
Okay.
And then the human is sort of the supervisor, says, okay, quiet down everyone, I'll take control.
So if the human grabs the wheel, it automatically lets go.
In all current driving systems, if the human wants to take control, they get control.
Mm-hmm.
There's no, very few situations in which an AI system will take control from a human without consent.
Would the automatic braking be one of those examples?
Exactly.
Okay.
Exactly. So when the danger of crash is imminent with a split second, where a human being can't possibly react in time,
Mm-hmm.
that's the only time where a car will take control.
Okay.
But in terms of saying, well, for example, you're too sleepy, or more importantly, you're too drunk to drive. Currently, we as a society, are not ready for AI to say, I will take control from here. That's
ethical then at that point.
Yes. Yeah. The questions of ethics are fascinating and interesting, and I think that's for public and for students and for everybody to discuss of how to approach these questions of ethics as these systems get smarter and smarter.
So let's try to wrap up in the next probably 3 minutes or so. Sure. We'll let the students answer some questions in a breakout room, and we'll come back and try to have about 5 to 10 minutes of Q&A.
Sure, sounds good.
Okay.
So another example is taking taking cars, and we have tens of thousands of runs like this. We're having here showing a black car, little MIT logo on it with blue lights out front. You see that's a single camera taking in the world outside. It knows nothing in the beginning, and it's tasked with learning how to avoid collisions.
So when it collides, it gives a feedback and says, you collided.
Yep.
And so then it makes weights that hopefully will prevent it from colliding in the future. Okay.
It's a binary classification problem of did I collide or not. And over time, it takes, so we're currently in the learning phases. It's very early work, but it takes tens of thousands, if not hundreds of thousands of crashes to learn how to avoid those crashes. So that sounds perhaps like a large number, but given that there's unfortunately 1.3 fatalities every year, 1.3 million fatalities every year, and there is about 100 times that crashes on public roads in the world. That's plenty enough data to train algorithms to learn how to avoid those crashes. Of course, we're doing it in the fun, safe setting of an MIT gym. Vehicle traveling at 30 miles an hour, crashing into cars, but where there's no humans being hurt. But this is the kind of questions we're struggling with. Because ultimately, in the autonomous driving situation, our goal is to save lives. 38,000 people die in the United States every year in traffic accidents. We want to decrease that number as close to zero as possible. And that's where AI can really help.
Absolutely.
And a quick mention, I think we could talk about this a lot, but where deep learning methods and machine learning methods can help in the supply chain, really the methodology itself is open to all kinds of data. As I mentioned before, the task is to collect the data, clean it up to a degree that machines can interpret it, and whether you're using machine learning generally speaking or neural network methods, then extract the features that are relevant for whatever the task is. So you can detect anomalies in disruptions in the data, so you figure out the patterns in the data enough to detect the weird parts, the things where something that seems wrong, anomaly detection. You can, of course, extend that data, as with natural language generation we looked at, to forecast the future. You can plan to the operation research kind of optimization, where you plan which areas based on previous data need to be replenished. And you can understand and visualize the role of the human inside this entire supply chain. And that's really what we looked at in driving. And we could certainly look at that in supply chain. Is how does the human make everything more complex? How do they screw it up, and how do we fix it?
Absolutely.
How the machine fix it?
So an interesting kind of tie back into the supply chain. When we have autonomous vehicles, I think that'll have a big impact on the supply chain, at least the logistics aspect of the supply chain. And so we'll kind of tag back to that in the Q&A section, hopefully.
Sure.
And then I think we're going to let the students go to their rooms. So we have a series of questions. So I think Arthur can put those up on the screen or ask them in your rooms. So if we'll go there, we'll try to spend roughly about 10 minutes there. So we'll try to come back at about 10:52. That's Eastern time, so we'll try to come back in about 10 minutes.
Great.